Hello, everybody. I'm Dr. Shafiq, and I would like to welcome all of you in this video session. In this video, I'm going to discuss about how to design slab-on-grade foundation on expansive soil. You already know that I posted a handout about expansive soil, and I'm sure that you got a chance to take a look at it so that you can understand why the soil will move because of the change in water content of the soil. Okay, so we basically have two different methods which are widely used for the design of slab on grade in high plasticity expansive soil. One of them is wire reinforcement institute method. The other one is PTI, means like post-tension institute method. Today, I'll be talking about wire reinforcement institute method because this one would be easier to do without any software. Okay, so let's start our discussion. I'll just try to share my screen with you right now. So first of all, we are going to discuss about effective PI. PI means like plasticity index of subgrade soil. Okay, so this design is basically based on the use of effective PI. Now, what is effective PI? Because you see the soil usually have different soil layers, and your plasticity index of the subgrade soil in each of the layer can vary significantly. Now, you have to find out a procedure so that you can use the equivalent or weighted PI for different layers. Now you can see that for equivalent PI calculation, more weight is allowed for the upper soil compared to the soil that's below the surface. So basically, to calculate your effective or weighted PI, the soil within the first 15 feet from the surface is important. Any soil below 15 feet, will not be count for this design method. Why is that? Because we know that basically the slab-on-grade foundation is applicable for lightweight structures, okay? Usually from 1 to 3 story building. Most of the time it's residential building. Sometimes it could be commercial building too. Now you can see here that for the first consecutive 5 feet from the top, we use a factor of 3. Okay, from 5 to 10 feet, we use a factor of 2. And then from 10 to 15, we take a factor of 1. And then try to find out the weighted PI. Now you can see here, this is a soil profile, which has PI 32 for soil A, which is extended from surface to 2 feet, from 2 feet to 8 feet. They have soil B, which has a PI of 40. And then from 9 to 10 feet, we have soil C, which has a PI 18. And from 11 to 15, we have actually, this one is extended to 20 feet, but we are going to count only up to 15 feet here. Okay, so if I use these factors, 3 for the first of 5 feet, 2 for the second 5 feet, consecutive 5 feet, and then 1 for the next consecutive 5 feet here. So I just wrote the PI here for each of the feet depth here. So this is 32, 32. Here, this is soil B. So this is 40, 40, 40, 40, 40, and 40. Here we have 18, 18, and these are the 48 for soil D. Now, if I multiply this PI with this factor, then basically this is your factored PI. Okay, so 32 multiplied by 3 is 96. That's the way I just put like all the factored PI here. And when I divide that factored PI, summation of that factored PI by the summation of this factor here, then I get the weighted PI here. Once we get the weighted PI, then basically there are some corrections for that, excuse me. There are some corrections if for two reasons. First of all, if the land has any slope or the unconfined compressive strength of the subgrade soil. Okay, so I'm going to discuss that one in the next slide. But before that, you can also see, you have to remember that one, like let's say for a particular soil layer here, this is, if the PI is less than 15, then this method suggests that you have to consider at least 15 for any intermediate layers which has a PI less than 15. Okay, so in this method, actually 15 is the lowest PI you can consider. Okay, now let's move forward. So effective PI correction factors, as I said earlier, there are two reasons that I have to correct my PI. First of all, the slope. If the land has a, like average slope, continuous slope, then basically we have to adjust our weighted PI. And then degree of consolidation. That degree of consolidation, that depends on the unconfined compressive strength of the soil. Now take a look here. So this one is actually figure 8 in their manual. By the way, I forgot to tell you that one, that I'll also post their manual so that you can take a look. The biggest problem with that manual that they updated that one with an addendum with the old one, so it's kind of a little bit difficult to synthesize by yourself. So you can see here that I started with figure number 8 rather than 1, 2, or 3, something like that. So the figures are not, are not compiled chronologically because they just added an addendum to the old one, okay, rather than doing the whole thing from the beginning, okay. So here you can see here, this is your slope of the natural ground, and this is your CS, okay. So CS, when there is zero slope, means like your CS equal to 1. If it goes up and up, then you can see your CS is increasing, okay. So that's one of the thing you have to consider. The second thing is the unconfined compressive strength. You can see when the unconfined compressive strength is 3 TSF, ton per square feet, then basically your C naught equal to 1. If it is less than that, then basically your C naught is smaller than 1. And if it is bigger than this, then basically you will see your C naught is higher than 1. Now you can see less than 1, then you can see your C naught can increase significantly there. But it's not that common that the high plasticity clay soil has lower than 1 TSF strength because of the swelling pressure. They usually try to swelling pressure, and during the shrinkage, actually they try to consolidate it as much as possible. Okay, so most of the cases you will see that the strength is more than 1 TSF. Now, my effective PI would be equivalent PI, what I got from the last page. Then I have to multiply the two factors like the CS and C naught from here. Okay, so CS is the slope correction factor and C naught is the consolidation correction factor. If these are 1, then basically your effective PI would be equal to your equivalent PI. Okay, now take a look for a simple example. My equivalent PI, let's say, is 30, and let's say the ground has 10% slope. So CS from this figure 8, you can see for 10, this is your CS is 1.1 and 6 TSF unconfined compression strength. So if you go 6 here, then you will see basically this one is around here, right? So your effective PI would be 30, which is your equivalent PI multiplied by the factor CS and then multiply by the factor C naught. So basically you got 39.6, which is almost 40. Okay, so usually the PI we always try to express as an integer. Okay, so you have to round it up. Now let's move forward. The geographic location of the construction site. Okay, this is very, very important because of the seasonal variation of rainfall and everything. So based on the seasonal rainfall, that how dry it could be and how wet it could be, based on that, we have a chart here which will actually show us the climate rating factor CW here. Okay, so you can see this is the map of the United States. This one starts from 15 here. This is 15 line here. This is 20 line here. And it goes from 15 all the way to 45. So 15 is the worst case scenario, means like it could go all the way to very wet. At the same time, in the same year, it could go all the way very dry. Okay, so in that situation, you can understand that the soil will try to shrink when there is no water there, and this one will try to swell when it will rain or like there will be flood there, right? So you can see the movement of the soil is maximum, like for the climate rating 15, and 45, the effect of like that swelling and shrinking would be minimum. But you can see here that our location in Texas, actually this is San Antonio, and Austin, actually this one is around like 18 here. For San Antonio, it's usually we consider that one 17. Austin is 18, Dallas is 20, and Houston is 25. Okay, so I just got that one from here. Now let's move forward. Loading condition. Okay, so since these are just like light building, usually from 1, 2, and sometimes 3-story wood frame construction, such as home and small commercial buildings, the assumption of uniform load works pretty well for this particular design method. Okay, we usually distribute the load all over the foundation slab. The second thing, if there are large concentrated load of numerous columns, then attention must be paid to the location of stiffening beam or thickened areas of the slab so that the load can be spread out. So most of the time, what we try to do is put the column at the cross section of two beams. Okay, that's the way we try to minimize the effect of stress concentration. And sometimes if it is not possible, then usually we try to design a column pedestal at the bottom of the slab so that this one will not create any problem. A building which are carried totally on columns need a different analysis from the uniform loading assumption. Okay, so primarily this one is based on uniformly distributed load, but I'll show you an example that where I'm also adding a line load along the periphery of the building, which is coming from the load bearing wall. Okay, so we are going to go there. But now I'm talking about the theory. I'll show you an example where I'm going to do everything, to show you how we use this theory to design. House loads. Most of the time, it's always better if you can calculate the total load that's working down there. Okay, dead load and live load separately. If not possible, then basically we can assume that for one-story building, the uniformly distributed load is 200 PSF. For two-story building, it's 275, and three-story building, that's 350 PSF load. Okay, but once again, you can see if the wall is load-bearing wall, then basically this one might have a line load at the exterior or at the periphery of the slab. So you might count that one separately too. Okay. So design assumption. Here is the design assumption. First assumption is saying that loss of support at the edge due to center heave or edge settlement. Okay, so you can see this is kind of like center heave here. So this one has lost support here and here. Similarly, edge settlement, because of drought, you can see there is some settlement, and this one has lost the support here and here. So in that situation, they are assuming that from here to here doesn't have any support here. So the slab is kind of cantilever here. Okay. Similarly, the other side, they have, also, and this is called the cantilever length. Okay. And the total load here will be taken care by this soil, which is in contact with the slab here. Okay. The second situation, this situation will occur when basically when you will see the lot of water is at the center of the slab. Usually for high plasticity soil, your hydraulic conductivity is very low. So when it rains, then it can go only few feet inside the soil. Okay, it cannot go all the way to the center of the slab. But many times we see if there is any breakage or leakage of the water line, then basically the situation can happen when the center will heave. Okay, now let's move forward with the second assumption, is that a loss support at the center due to the edge heave or center settlement. Okay, so here you can see this side is either like the center has settled, or actually this one is more common, edge heave, because of the rainfall. Okay, so you will see that basically it can happen that there is no support here. But over the years, after a lot of experiments and observation, we just realized that most of the cases, actually the edge of the slab is more susceptible to change of the um, shrinkage and swelling thing. So you can see here, like because of the drought, like this soil has shrinked here and shrinked here. So you can see some part here, it doesn't have any support. And we already told you that length of this cantilever, we call that one LC, okay, lowercase LC here. And here you can see when it's gonna rain, then basically the soil very close to the edge will be saturated or will try to get more moisture from the rain and they will try to swell. So basically you can see that in that situation we are having higher swell pressure than the normal soil reaction here. Okay, so they will try to create a arch in this direction, like and creating like positive, like moment. Here you can see this one is hanging like a cantilever, and it's kind of trying to have a lot of negative, like bending moment on the slab. Okay. Now, based on the PI, like you can see PI and the climate rating, you can just go there and try to find out three things from this chart here. Okay, first of all, your LC means like your cantilever length. Okay, because the distance from here to here, because of the seasonal variation of moisture. Now, definitely this one will depend on like which part of the country you are talking about. If you are talking about 15, then basically this is the worst case scenario. So you can see for a particular PI, you will have the highest cantilever like length here, okay? So from there, you can also see they are giving you the S. S means the spacing between two stiffen beam on the slab. Okay, the maximum distance you can have, that's actually your S. And you have also ASFY. This one also give you for your reinforcement design for the slab. So basically, if you know your PI and your climate rating, then basically you can get three data from here, your LC, your maximum spacing, and ASFY from there. So we use this one to calculate that how many beams I require for the slab, and at the same time, how much reinforcement I need for the slab. And then basically you have to calculate your moment, and then you have to see that how much reinforcement you need for your beams. Okay, so let's move forward. So correction of LC. The LC you got from that chart is basically for a building which has like length and width more or equal to 100 feet. If this is less than 100 feet, then basically you have to make some adjustment of your LC. That's what we are going to do here. So the cantilever length IC obtained from that previous page is for large slab where L is greater than 100 feet. Okay, if our actual length is less than 100 feet, then basically we have to adjust our LC, which is actually LC multiplied a factor K. Okay, K is a factor, depends on the actual size of the slab. So you can see here, this is actually figure 6 in that manual. And you can see if your length here, this is actually length and this is width. Okay, length and width. If your length is 100, then basically you see your K equal to 1. If your length is, let's say, 50, then basically your K would be almost 0.96. Okay. So for an example, for a 60-30 building, let's say I got IC from the previous page, like 7 feet, how I can adjust that one? Because this is not 100 building or more than 120 building, then I don't need any adjustment. But I have like 60 and 30. So first of all, if I take the 30 side here, then basically I get that value from here, which is 0.92. Okay, so KS means like the short side, or long side is along the length and short side is along the width. Okay, so K as in the short side is 0.92. And if I take the long side, which is 60, then basically you can see here that this one is going here. So actually your K in the long side would be 0.97 from here. Okay, so my adjusted IC for the short side would be 7 multiplied by this factor 92, which is 6.44, and adjusted LC for the long side is 7 into 0.97, so this is 6.79. Okay, so that's basically like the adjustment for your LC. Now we have to, like do the design calculation. First of all, they give you these equations here. You need to use this equation to find out your moment. We are not going to use this one there or this one for our design purpose. You can use this one, but actually they provide another equation so that your deformation would be less than 1 over 460. Okay, so you don't have to worry about your deflection once you follow that equation like this one here. So the depth of the beam determined from the following formula, which is a cube root of 664. M is the moment, LC is the length of the overhanging part, divided by B. B is the sum of width of all beams in any particular direction. Okay, so if you use this equation, then basically and find out your depth of the beam, then basically you will be fine with the deformation automatically. Okay, so you don't have to check that one anymore. And this calculation will have to perform in both, like in long direction and also in the short direction. Okay, so you already saw that my overhanging portion is changing in the long direction, in the short direction. So your moment will also change, and that's why you might have a different value of your D, and your reinforcement might be different too. Okay, so that's basically your theory of that one. Now I'm going to show you an example problem. Okay, this one will clarify many of the things that what we have been discussed so far. Now, if you take a look, there is one problem, example problem given in the manual. Just take a look there too, okay? Because here we are just going to talk about the foundation engineering part, but there are a lot of other things involved in foundation in terms of your reinforced concrete design thing. I'm not going to discuss that one here, but they showed that one in the example problem. If you have any problem to understand that reinforcement design, please let me know. I can just help you. I know, like, I'm not going to ask any question from that part here, but for your senior design, I know, like, you might have to do the reinforcement design. So many times I see that students are suffering. So if you have that kind of problem, please feel free to contact me, or you can just talk to your concrete professor to help you out. Okay. Now let's see the example problem here. So a single-story residential building will be constructed in Manor, Texas. Manor is very close to Austin, actually. And the plan of the building is shown in figure 1. This is the plan of the building. The boring log of the site is also included. Actually, in next page, I'm going to show that one to you. There is an average 6% slope on the surface of the land. The unconfined compressive strength of the soil is 3 TSF. The line load from the load-bearing wall at the periphery of the foundation is 300 pounds per feet length, and the uniformly distributed load on the foundation W equal to 200 pounds per feet square. There are 3 internal columns on the foundation which are 1 feet size, and each of the columns carries 10 kips load. Design the slab-on-grade foundation following the WRI method. Okay, so this is basically the figure here. Okay, now if I go to the next page, they are giving you the boring log at the site. So you can see from 0 to 2 feet, this is fat clay and PI is 35. From 2 to actually 8 feet, these are lean clay, low plasticity clay, which has 24 and 32 plasticity index. And from 8 to all the way 20, the plasticity index is 39. So it's kind of a mix of high plasticity and low plasticity clay, okay? But most of the cases, it's a requirement that you have to go at least 20 feet for any residential or light commercial building, okay? So most of the time they usually go for 20 feet, but for WRI method, we don't need that far. We actually need up to 15 feet. So I'm going to show you how to find out the equivalent PI based on this chart here, okay? So that's your equivalent PI calculation. You can see from depth 0 to 1, my PI is 35, right? 35. And second feet is also 35. From second to 8 feet, it's no, from second to sixth feet, it's like 24. So 24, 24, 24, 24, okay? Then from the sixth to seventh, actually from here to here, that's actually 32. So this is 32. And then all the way from 8 to 15 is 39. Okay, there's the 39 here. Now I have to use factor 3 for the first 5 feet, then factor 2 for the next 5 feet, and factor 1 for the consecutive third 5 feet. Okay, so if you multiply that one with 3 with 35, this is 105, and you just multiply all those things here, and your equivalent PI has to be 953 divided by this 30, which is almost like 32. Okay, so your equivalent PI is 32. Now, they said like that the land has a slope. So basically, we need to correct our PI, okay? So first of all, you can see here, this is for slope. So for our particular case, the slope is 6%. So if you go here and draw that line from here, 6, so this one will give you that value of your CS, which is basically 1.05, okay? Now the second correction would be from the QU, means like your unconfined compressive strength or your undrained shear strength, okay? So here is your figure. Now our unconfined compressive strength for our case is 3 TSF. So if I come here and draw that line and try to see then basically your C naught is 1. Okay, so what would be my corrected PI then? My corrected or effective PI is 32 multiplied C naught multiplied by CS. So this one is 33.6, which if I round it up, that would be 34. So 34 is my effective PI. Once I know my effective PI, then I have to see like what is the climatic rating. So you can see Manor is close to Austin here. So if I draw a line here, that's basically kind of 18 from there, right? So basically the location of the residence is in Manor, Texas. So the climatic rating is 18, okay? Manor is actually very close to Austin. So they usually use 18 most of the cases. Now the design parameters, once I know my effective PI and the climate rating factor, then from this particular chart given by them, which is figure 5, I can just find out these design parameters here. Okay, so my PI is 34 and my CW is 18. So you can see this is the line for my IC, my S, and my ASFY. Anyway, let me tell you one thing is like why they already have a line here at 18. That's because the head office for Wire Enforcement Institute is in Austin, okay? And the climate factor there is 18. So that's why they put that line over there. Now you see here, so what would be your IC here? You can see this is 6 and this is 7. So from here to here, I assume this one is 6.3 feet. And if you see the S here, S is the maximum distance between two beams, so which is almost like 17 feet, okay? And then you can see your ASFY. I assume this one is 4050 because this is 4100 and this one is moving this direction going up, okay? Once you get these three numbers here, then basically you can start doing some calculation and see what would be the number of beams in each direction and what would be the depth of the beam in each direction, and as well as some other things too, okay? Now, first of all, we need to do the rectangle selection. Means like, if this is my plan of my building, how I can design like when this one is a little bit irregular here and here. Okay, so what usually we do that first of all, you have to draw as many as rectangles, as big as possible, okay? So you can see this is your rectangle 1, then you can see this is rectangle 2, and this is rectangle 3. So which one is the biggest here, okay? So the biggest is definitely rectangle 2. So this is my rectangle 2. And you can see this is 73 feet long and 41 feet wide. So we have to design that one based on this particular slab. And then we can use the same, beam spacing in the other part. And we can just move forward, okay? So now let's start. The IC correction factor, okay? No, sorry, LC correction factor. LC is the length. And now you can see you don't need any correction if your length in the long direction, which is, we are calling that one L long and L sharp, okay, LL and LS. So our LL is 73 and LS is 41. So basically both of them are smaller than 100 feet. So I need some sort of adjustment on that, right? So I have to find out, hey, what is my K factor for that? So let's move forward. So first of all, this is the chart here. I have 73 here and I have 41 here. So I have to find out my K, okay? So let's say for LL73, then basically I draw a line here, and from that line I just go here, and this is basically 0.98, okay? This is 0.98. That's in the long direction. How about in the short direction? In the short direction, our L is 41. So if I draw a line from 41 and go here, that's basically 0.94. Okay. So once we get my KL and KS, then I can find out my LC in the longer direction and in the short direction. Okay. So here you can see I got that one. My LC was 6.3 because of the adjustment. I'm multiplying with that K. So in the long direction, my ICL would be actually 6.17 feet. And in the short direction, that would be 5.92. Once again, LC means that overhanging portion, which will be hanging when the soil will shrink, okay? Now, number of beams in each direction. So first of all, let's start with the long direction. So that's the way the maximum spacing is 17 for our case. So we have LS, so 41 divided by 17 plus 1. So always you have to make that one a round number because your number of beams cannot be a fraction. Okay, so I see that we need at least 4 beams in the long direction. Okay. Similarly, if we try to do that one for short direction, then this one would be LL by S. S is the maximum spacing, 17 plus 1. So we need like at least 6 beams in the short direction here, okay? Now, loading on the foundation. First of all, the distributed load is 0.2 kg per feet square, which is given, and the line load is 0.3 kg per feet, which is also given, right? Now we have to find out the moment, that how much moment this one will create in the cantilever when the significant portion of the soil will not support the slab, okay? So I'm trying to show that one, the drawing here. Actually, you will not see that one over on the manual. I just tried to show that one to explain that how they got that equation from there. So you can see this is my overhanging portion. We have soil here, soil support here. From here to here, I don't have any soil support. So we call that one the cantilever length, right? So that's from here to here. Now you can see this is my uniformly distributed load, and this is my line load from there, which is actually, if you see the figure over there, you will see the wall is 1 feet, like the width of the wall is 1 feet. So that's why I just put that one at the centroid. So the distance from that one, from that end is 0.5 feet, okay? Now I'm gonna change that distributed load and this load here. So if you think about this slab in the other direction, this one is, because this is the longer direction. So other direction is, this one is 41 feet, right? Which is LS, 41 feet on that direction. So if I say this is WL per feet, So basically the total would be WL into LS, that many kips total, right? Similarly, if I change that uniformly distributed load, which is W, so from here to here is LC, and in the other direction is LS. So the total load would be W into LC into LS. And this one is definitely working at the middle of from here to here, right? Because I change only from here to here. So this is the distance of the resultant force here. Now you can understand where the moment would be maximum, definitely at that point, right? So if I take a moment here, then basically you can see that moment in the long direction is basically this load multiplied by this distance and this load multiplied by this distance from here to here, okay? So you can see this one is basically WLS ICL, and then again multiplying the distance here. So LCL, that's LCL square by 2. And then I'm adding this one here. So if you don't have any line load, then basically you don't have to add that one, okay? So you can see WL, LS, and then LCL minus 0.5, that's the distance from here to here, okay? So if I plug all those values here, then basically I get a 226 kip-feet moment, negative moment actually, right? You can see here, this one is trying to bend like this. So this one is basically negative moment, which is 226 kip. Now, the same way we can do that one in the short direction too, right? So in the short direction, these parameters will change a little bit because now we are talking about LCS direction. So if you calculate that one, then basically you got the moment in the short direction is 375 kip-feet, okay? Once you get that moment, actually you have to design based on that moment, that how much reinforcement you need, and at the same time, how much depth of the foundation you need so that your strength as well as your deformation, like or deflection is within the limit. Okay, so that's why they propose this relationship to you to find out your D, which is cubic root of 664 M LC divided by B. So you can see M is the moment, LC is the cantilever length, and B is the sum of all width in inch. Okay, this is kip-feet, this is feet, this is inch. So I'm trying to find out my D in the long section, I mean in the longer section. So you can see in the longer section, actually my LC is 6.17, and I have 4 beams, and I'm assuming each of the beam is 12 inch here. So basically I'm getting my D is 26.81, let's say 27 inch, okay? So I'm doing that one for short side, okay? 664, that's my moment in the short side. And then this is my LC in the short side. And in the short side, I have 6 beams, and each of them is 12 inch width. Okay, so its total is 72 here. So if I calculate that one, my DS means like depth of the beam in the short side is basically 28. Since they are very close to each other, it's always better to use the same depth. Okay, so we are going to use 28 inch in both direction. Okay, 28 inch in both direction. Now, definitely you have to now calculate that how much reinforcement you need for this one. And once again, I'm not going to discuss that one here, but there is a example problem in the manual. You can take a look there. If you have any question about that, you can definitely talk with me. Okay, now let's see here. So actually there is some portion here and here, but you can also use the same, continuity of that beam in this direction too. So you see, like I have 4, 1, 2, 3, 4. In the longer direction, I have 4 beams here. In the shorter direction, I have 6 beams here. Okay, and now you can see the maximum distance was between the beam was 17 feet. But actually you see when I make that one like 3 equal sides, that's actually 13 feet 4 inch center to center. Okay. Similarly here, I see that this is 5 here is at a rate of 14 feet 5 inch center to center. Okay, I could go maximum 17 feet, but basically when I tried to make that one as a, like round number, then basically that gave me actually 6 beams here, and that's why this distance is a little less here. Okay, if I want to see, let's say, a cross section here, then this one looks like this. Okay, so I have 1, 2, 3, 4, 1, 2, 3, 4 beams here. This is the distance from, and this is the center to center distance, 13 feet 4 inch. And from here to here is actually, this is not center, so this is actually 12 feet 4 inch. And this one is 28 inch here, and this one is 12 inch each of them. Okay. Now I didn't show you, I tried to show you the actual reinforcement here, but I didn't write it anything here because you have to calculate that one and try to make sure that how many reinforcement you need in these beams and as well as in the slabs. Okay. Now one more thing you have to do here, they didn't show that one in your in the manual, but I see that many times for your senior design project, you have to see that you have columns, okay? And this columns is resting on the slab, okay? So what happens, the most common thing is like the column, if it has like very high loading, then basically this one will try to punch through the slab. So many times, if we see that the punching shear could, cause the failure, then basically you have to design a pedestal below the column so that it cannot punch through that. Okay, so that's the formula here, that I assume that D is the required depth to protect punching shear. So you can see the perimeter here where the actually your punching shear that propagates 45 degree. Okay, so if total depth is D, then basically you will see the average midpoint of that thing is actually D by 2. Each side D by 2, D by 2. So this one from here to here would be L plus D. And if you try to see that the failure occurs all 4 sides, then basically you just adding like 4 multiplied by this one, which is actually 48.4 D. And the load in each column is 10 kips. Then I'm adding that one, like multiply with that factor 1.4. So make that one 14 kip, because I'm going to use the ACI code, which requires that you have to multiply with the factor of that thing to make that one, like your factor load. Now from that ACI code, this one is saying that your phi VC had to be equal, greater than or equal to your VU. So we have our phi VC is equal to phi 4 root over a prime c, b naught d. D is the depth, b naught is basically the perimeter where the failure will occur here. Okay. So if I solve that one, then basically the required depth has to be 1.4 inch. But actually my slab is 4 inch. Okay, so much higher than 1.4 inch. So I don't need any pedestal here to design because the slab will be able to handle that shear. Okay, but many cases you will see that when your load on the column is very high, then basically you might have to put some pedestal there. Okay, so that the let's say here, if your D is, let's say, 6, which is greater than 4, then basically you can see here that actually this one is total length here would be 12 plus 6, so that's 18. So we have to put like a little bit, maybe like 2 feet size pedestal, which is more than actually 6-inch depth in the more than 6-inch or 6-inch depth. So below the, like below the actually the slab. Okay. Anyway, so that's basically your check for punching shear. And if you have any question about that, please feel free to contact with me. And I'm going to give you one of the problem for your homework so that you can just practice that one and see that how this one works. So thank you so much for watching.